record. What next? Okay, so here are the files. So I downloaded those files on my computer, but you can also do the same thing there because you have access here, right? If you log into the Canvas page and you open this folder, this link, and you have access to the same files. So as the lecture goes on today, I will add more files here so that you have real-time access to those files. So for now, we only have 3 files. If you remember last time, we talked about the difference between the MIDI format and the music XML format. So we will continue there. So after you download these files, if you already downloaded MuseScore, you can open this with MuseScore. So my computer is in Chinese, so it doesn't matter. So if you downloaded MuseScore, you can open those files in MuseScore. And my files, my MIDI files and the music XML file are defaulted to open with Music Score, Music Score Studio. And this is a free open source music notational software. Okay, so this is the MIDI file, right? So this song is the Maple Leaf Rag. And let me open the music XML file. Okay. So in terms of how the files are encoded in computer, we'll get to more details. Maybe in our later half of the lecture or next lecture, depends on the time. This time, let me play those files first. Okay. So first is this well represented sheet music in music XML. Repeats. And let me play it in the MIDI format. So you can hear that there's no audible difference between those two formats when I open them in the same software. Okay. So you can see here it also repeats, right? So from here it repeats the entire paragraph from the beginning, but there's no like repeating mark because this is in MIDI file and everything is encoded, in this temporal scale. So it doesn't have this complicated notations as in the music XML. So what we will do now is that because those two files sounds the same, we can export the audio, right? So now we can watch or read those scores, but we don't have the sound. So in order to listening to the piano sound, we can go to the file and export. So there are different formats you can export. You can choose either MP3 or WAV. So WAV actually give you a larger file with higher quality, and MP3 is a compressed file with smaller size, but it doesn't preserve the audio quality that much. So I'll export this as WAV audio, and you can see here this sampler rate. So we'll talk about these audio kind of properties later on in more details, but you can choose different sampling rates. A typical sample rate is 44100 Hertz. Means there will be 44100 samples per second, okay, in the audio file. So let me export this. Okay, so this is the wave, and okay, this I'll export this to our lecture file folder. So it takes some time to do this, but when it's done, yeah, I'm able to see the file here. This is in the WAV file, audio WAV file. Anyone know WAV file or anyone worked with WAV before? Really? Okay. Okay. So let me check. Okay, it's fully exported. And for the audio file, because you are listening to this, you can open it with any default, music playing here. Right? It's the same audio that we just heard in the music score. So this is the file we just have. Let me rename this to music score, okay? Because this is generated by music score. Okay. So now, what we will do is that we'll use another software, which is Ableton Live. So I don't know if you have Ableton Live or not. If you never downloaded Ableton Live, you can have a 3-month free trial of this software. But yeah, if you want to use this longer, you have to subscribe and pay. Okay. So it takes some time, but you will hear an audible difference when you open the same MIDI file in different softwares. So actually, the Ableton Live is able to keep more details of the file. And we'll get more into this. Why? Like what kind of information was discarded in mute score but kept here, and why it sounds different here. So to do this experiment, so here is this interface of Ableton Live. Okay. Now I'm going to open the file create. Okay, create, import MIDI file. And we are going to import the same MIDI file here that we use for our lecture files. Okay. So this is Maple Leaf Rec MIDI. Let's open it. Okay. So now here you can see it's important. And this is the piano roll. If you remember our slides here, right? Different notations, piano roll. It looks like this. So actually, Ableton Live uses piano roll representation for the symbolic music. Let me see if I can get this, enlarge this part so that you can see better here. Yeah. Yeah. So this is a piano roll. But if we play it now, there's no sound, right? The reason is that actually in MuseScore, when you open a file, it gives you the default instrument. So that the instrument here is piano actually. I think you can actually change the piano instrument here. If you go to settings, not really. But yeah, there are some place you can choose the different instruments so that you can play the same score using different instruments. But because the piano is encoded in the MIDI file. So the MIDI file tells MuseScore that this sheet music is composed for piano performance, so that it defaults piano as these instruments. But in Ableton Live, because there are so many different instruments, you can see here, right? If you go to instruments, there are so many different types of instruments, and because the software is, yeah, so it kind of says like, I don't know what instrument you want, and you have to choose your own instruments. That's why in order to play this thing, the music in Ableton Live, you have to handpick your own instrument. Okay, how to do this? Okay, so here is drop an instrument or sample here. Because we're using piano, we can search for piano. Sorry. Okay, so even for piano, there are many different types. You can see piano keys, clearing, even electric piano. Yeah, let's listen to this. This is kind of another one. Oh, this piano you. So there, even for you tell the computer that the file is uses piano, it doesn't know what kind of piano you are referring to, what types of piano is this. And there are some FM's pianos, right? Okay. For our purpose, we want the most classical piano sound because this is a classical composition. It's played in this original real piano, so we don't want this synthesized or electronic sound here. So that we will use this one, grand piano. This sounds is like the real piano. Okay, so let's drag it and drop it here. Okay, now we have our sample or our instruments to play the music. Yeah. Why I cannot enlarge this? Difficult, right? There are different parameters here. You can tune those parameters, tune those tubes to change the sound, but I will keep it in this original format. Yeah. Now let's try to play. Now this one. Now there are two tracks. There are two tracks. Okay, the left hand and right hand. So it also captures these two tracks in different tracks here. So let's see if we can play this. Okay, it's weird. Well, oh, probably because I didn't drop the instrument here. So I dropped the instrument for the first track, but I didn't drop the instrument for the second track. So you need to do this like twice to make sure the two tracks all like sound together. Yeah, let's do this now again. Right? I don't know if you have a feeling that it sounds better than music score. Probably not. Maybe you already forgot how music score sounds, but we will do a comparative study very soon. So yeah, let me enlarge this. You can see these piano rolls, how it works. Let me maybe. So there is a score follower. It follows the piano roll and it plays the notes. Okay. Okay, so this is the piano roll. And in terms of this, let's talk about this later on. So now what we will do is that we will export the audio generated by Ableton Live. Okay, so let's export audio here. Okay. So there it use sample rate. Let's choose the same sample rate as the audio file generated by MuseScore. And encode PM and wave file is the wave B depth. Yeah, hopefully I'll talk about this next week. Okay, we talk about digitalization of sound. We'll talk about the sampling rate and B depth. Yeah, a lot. But now let's just use this default settings and just export the audio. Okay. So let's name it Maple Leaf Rag. No MuseScore, but Ableton. So now what I'll do is that I'll upload these two files to you so that you have access to them on your own computer if you don't export them by yourself. Yes. Yeah, a little bit slow. But I think we have access to this now. This MuseScore this is this should be able to. Let's listen to this. Okay. Okay, great. Yeah, it's still uploading. It will be there soon. So next, what we will do next is that we are going to use Audacity this time. Okay, Audacity is also a free open source software for recording, and we will use Audacity a lot in this course because this is comparatively easy to use, and you don't need to know this lower level or higher level programming languages. You don't need to know Python, MATLAB, or C++. It is easy to use, user-friendly, and has many functions that it will be helpful for me to illustrate some concepts. So this, I will recommend you to download this software, yeah, if possible, because we are going to use this a lot, especially when we're dealing with the audio features, yeah, in the later part of the course. So now I opened Audacity, and let me open the file that we just. So some of my system are in Chinese, so I'm sorry for this. Yeah, let me see a question. Yeah, how do you download this? Let me see. Oh, a lot of browsers here. So you go to the your canvas and you open this page in the modules. Okay, modules, the first week, and this is the main page. Yeah, Zoom is just like this. But if you go to softwares, you have access to all those. So Audacity is here. Yeah, there is free downloading. Yeah, download Audacity, installs with no extras, and also this one. Oh, yeah, this is the like very easy. Just install and use. Yeah. And also MuseScore is here. It's also free to download. Yeah, and use. Audacity, Ableton maybe takes more more time, and Jupyter Notebook. Yeah, Jupyter Notebook is not really required. But if you want to run my code, yeah, because I will show you the code here. I'll run it in real time so that you know how it looks like. But if you want to run it yourself, you need to install Jupyter Notebook here. Yeah, it's kind of slow because I opened too many softwares now, I guess. Well, let me go to our lecture files. Yes. This is new score generated audio. Let me open. Okay, so you can see this is the stereo audio. It has 2 tracks. Okay, the stereo, which means if you use the headphone, right, it has left ear and right ear. This is two channels. But there is also, if it's mono, which means it only has 1 track, which means your left ear and right ear hears the same thing. Here it's divided to it's stereo, divided to 2 tracks, and you can visualize the waveform here. This is the real kind of the recording or the real live representation of the waves you hear through your ear. Okay, so we can play this. Okay. Maybe let me enlarge this so you have a. Now let's also import the audio. Let me see, what's the question? Okay, the vertical axis represents amplitude. Yeah, the axis is time. You already know this is the amplitude. So you can see it's from -1 to 1, which means like how loud. When you come here, this sound is louder comparative to the sound here, right? So maybe I can complete here so you can compare the the dynamic. Yeah. So this is loud, this is quiet. Okay, let me do this from here. Right. Then he see here, the largest one only reaches 0.5, it seems, but we can change it. I'll show you how to like compress or amplify this the sound later on. But let me actually import our next audio first. What's this one? Okay, this is what we just got, yeah, from Ableton Live. Incorrect. It's ASD. Oh, interesting. Really. Yeah, it should be correct. Let me do it again. Yes. Okay, so this second track is the audio generated by Ableton Live. So if you click solo here, you can only play this one track. Okay, let me play this. No. From the beginning. Then, yeah, seems difficult. Don't know you. Right? If we solo this track, we can listen. Okay, again, this one. Yeah, how do you feel? How do you feel about listening to those two audios? They're different, right? First of all, different. And I feel the second one sounds like much better than the first one. The first one seems like the notes are connecting to each other. It's not like really separated, and doesn't have this sound, like some certain effects. I cannot name them, but I can feel it when I listen to music. Yes, yeah. Yeah, especially if you read the file, the audio waves here. Let me enlarge this. Yeah, but you can also tell. So here there's no like kind of clear delimitation between those nodes in this file. But here, yeah, you see this dynamic range has changed much more, and the overall gain is larger here. So okay, so back to this topic. So what if you want to like enlarge this gain to this level, right? Because you can see here the largest amplitude is nearly like 0.8 here, right? 0.8, but here is only 0.5. What you can do is that you can go to the effect and amplify. Okay. amplify dB. Yeah, let's just apply. Okay, yeah, it just amplifies. And let's play this now. Yeah, the chorus doesn't change, but it might be louder in your ear, if you're sensitive to this. So whatever, this is what we visualize the wave format in Audacity. Okay. What else? Anyone? Everybody's following? Any questions here? Maxwell, maybe. Okay. So next, what's next? Let me check this first. Yeah, WAV file. So you have access to this folder and you can download those WAV files here. Okay. So next, before we dive into those the details of MIDI formats and music XML, let's talk about this. Okay. So here is another audio or another thing. It is played by real human. So let's listen to this. Because we already listened to the right the sound or the audio from MuseScore from Ableton Live. But what about the real human? So if music performer play this song, how that sounds like?
Nature's Recipe knows a
Okay.
dog's best life is measured in wags. That's why every
How do you feel about this one? Right. So there is more dynamic timing and the nuances that the human performer, like indulge in this song. And the better the performer is, the more he can express through the same composition. So what we can do is that we can actually download this audio. But I'm not doing this in real time. Here I already downloaded this same audio file. Which is here, I believe. Performance, okay. So let me move this thing to our folder and also upload this, okay? So that you have access to this one also. And we will open this in another track here. File, import audio, performance, open. Okay, so now we have 3 tracks of the same composition but different audio files. So you can see the same sheet music can generate different audios, if it's generated by different softwares or played by different people. Okay, this one is the performance. Let's listen to this. Let me probably delete the first. Yeah, it's quite slow. Yeah, I hope the software doesn't die. But you can see here there are some red marks. So these things actually indicating that the dynamics are over 1 here. It is exceeding 1, and it has to truncate. Okay, it cannot be exceeding 1. So the real audio might be exceeding 1, but it has to truncate this to 1 because these are strict -1 to 1 here. Well, it seems it doesn't work now. But whatever. So this brings us a new question or a new field to really think about. Let's say we have the performance, but how do we get the symbolic representations, right? For many songs, if you don't have the sheet music, you only have the audio. And for human, you can do this called transcription, right? So if you learn music, the first course for you is to listen to music and write down the notations. It's called I don't remember the name. It should be called transcription. Yeah, you have sightseeing course and you have transcription course. Sightseeing means when you read the sheet, you can sing it through your voice. You can create audio from the sheet music, and you can also listen to the audio and write it down on the paper in the using music notations. So actually, human. Yes. This is what I'm going to talk about now. Thanks for mentioning this. However, it means human, we have the ability actually to, to transform between the two kind of forms, right? Either it's in audio or it's symbolic. And only trained people or trained musicians can do this. For me, like it's kind of difficult if things get too complicated. It's difficult for me to do this full transcription. But if a well-trained musician, you can do very complicated transcriptions. But the question is, how computer can perform this task, right? So this task from audio to symbolic. But we already talked about the symbolic to audio, right? Using softwares. And this is like you find some instrument and you play the notes, and there's some programming here. But how do you do this inversely from audio to symbolic? So this is more complicated or more difficult. The thing people do this field is actually called music information retrieval. Means you retrieve information from the music recording. So here, this is the waveform we just see, right? In the Audacity. Okay, so my Audacity doesn't work. Well, okay. So this is the audio recording, and this is transcription you get. So you won't go from this phase to this phase using the computer. Actually, it is a pretty difficult task, and people spend like decades, 20s, even 50 years in, and even nowadays, like people still like working on in this field. So we will talk about neural networks, but before neural networks, there are some analytical method people use for this task. So here is a paper on this task. I already uploaded to our page. Yeah, this is the paper. It's called music signal processing. Yeah. You can read it in detail if you are interested. There are many technical details. Probably be difficult for you. But here, let's go through this paper together. Okay. It's a long one. Okay, so here is the audio form, and this is the called spectrogram. Okay, so this is a way of translating the audio in from waveform to the frequencies. So from time domain to frequency domain. These are the frequencies, means the pitch, right? Like when you play music, it has different pitches. Piano it has different pitches, and the pitch is basically represented in the frequency domain by Fourier transform. So it's difficult to tell which notes you are playing here, right, from the waveform. But if we change the basis and transform this to the Fourier, to the frequency domain by Fourier transform, we can easily tell the fundamental frequency so that we can determine the pitch. Yes, this can be done here, but let me debug. So. Okay, I think debug is also one part of programming. But maybe let me do this later on, whatever. So actually you can perform this in different, if you use MATLAB or Python, this program language, this will be, you need to write the functions and you can perform this. I'll show you it in our later lectures. But you can also do it automatically, immediately in this software. So there is some already written programs that you can use. I'll talk about this after our break, okay? After I fix this this problem. But let's continue with this now. So music representations. So here you have the notes. You have the the letter representation. We talk about the ABC notations, and here are the MIDI numbers, right? Indicating the pitch here, and the frequencies here. Okay. So spectrogram. So this is the function. Yeah, how do you perform fully transform? It involves some complex numbers, right? Operation here, and if you major in electronic engineering, you should be quite familiar with this. And log frequency spectrogram, yeah. I probably get into some of those details in our future lectures when we talk about the audio processing. But for now, let's just skip this part. And chroma. So chroma is actually a music. So previously we talked about the spectrogram here, right? Spectrogram or log frequency spectrogram. So this is for the audio. So all the audio, like sound, like the voice, the sound, the speech, any audio, any sound can be represented in waveform and spectrogram. But chromogram is something specifically designed for pitch, right? Pitch specified music, which means if you use chromogram, you can get those pitches, right? This C sharp, D, B. And this is a musical feature that music researchers use a lot. And if you get the chromogram, you can do a lot of applications. Okay. Here is the score, the music score. And from the score, you can generate this waveform. And if you visualize this waveform in the frequency domain using chroma, you can see, right? These are different chords, different frequencies, different pitches here. The x-axis is the time, and the y is frequency. Okay, so here you can see it gives you the pitch, right? C, C sharp, D, and you can tell where is this chord. It should be C, E, and A, right? The chord is C, E, A. So applications, once you get this chroma representation, what we can do is chord recognition, right? We can recognize which chord are represented in this piece, in this score. Like this is a waveform, this score, this is chroma. And you can determine like, right, what notes it is playing in this audio from this, the reference, this diagram. Okay. So, and we can also do audio matching. So this is for the pitch identification. But here it's also about tempo and beat, because music is temporal, right? The task is one. So there are two tasks. One is vertical, one is horizontal. So the horizontal one is about the chords, but the vertical one is about timing, time and beat. So there's something called onset detection. You need to determine like when the note was priced, right? It's like this. If you have some well separated waveform like this, you can see the onset here, right? When the note was hit, the onset. Directly processing and interpreting the audio wave data into the MIDI notes. Yes. So Yeah, audio processing actually basically means the transformation from wave domain or time domain to frequency domain, right? Because speech recognition is a huge field that people are more interested in speech than music, right? But for music things or music scores, music related audios, we also need to do this, another step of interpretation or processing to extract the information from the audio into the symbolic music representations. Okay. So here you can see, because this, I don't know what is this, how it sounds like, but it is clear, there is clear delimitation here. So you can, even from the waveform or the time domain, you can clearly tell when is the onside, right? So onside is the where the highest or the largest amplitude was. So this onside detection and a novelty curve. So this uses novelty curve, so a kind of analytical tool. So you have the audio and you do some numerical computations on the audio, and you kind of compute the onside. Here, because this is the traditional ways before neural networks. Okay, how people compute or how people identify the onside of the nodes. Okay, so here, this is a score, audio, and the spectrogram, and this is the novelty curve. Okay, from the novelty curve, you can, when the curve kind of gets sharp, this is indicates an onside. Yes, yes. There are also beat here, periodicity analysis and tempo estimation. So there is beat matching, yeah, beat estimation here. Later on in this paper. Cool. Yeah, beat tracking here. Yeah, this is definitely one of the applications of onset detection. But onset detection is also important for transcription, right? Like when you transcript an audio to the score, you need to know when, right? When the note was pressed in order to do the transcription. But yes, tempo, beat tracking and tempo estimation is definitely, yeah, one of the applications, important applications for onset detection. Yeah, great. So here, if you have kind of periodic or continuous onside of those nodes, like you can see the duration or the intervals are kind of similar here, right? Kind of periodic, and it has the same intervals here, so that you know it has a fixed tempo, or it's a rhythmic, right? It's rhythmic, and it's a musical feature of having rhythm, of having beats and tempo, and you are doing this periodic movement, yeah, in the music. So here are many formulas, details. Let me skip those things. And this is it's talking about how you detect those onsides using the novelty curve. And bit tracking, of course, like how you determine the BPM, right? Beats per minute, using computers, and also applications here. Yeah, so this is a bad estimation. This is a good estimation. Timbre and instrumentation. We're not going to talk about those for now. But if you're interested, yeah, just read through this paper. It's a good one. And another thing I want to mention is that maybe later on, okay, it doesn't work now. But yeah, after our break, I will talk about how to perform this transformation in Audacity by just one click, and some other features there. Okay, so let's continue with other materials. yeah. Okay, it works. Okay. So simply speaking, we can refer to this graph. So right from the audio wave file, we perform some digital signal processing, and we get this chromogram representation where we can identify those where the notes are, what are the chords, and also the onset, right? So obviously this chord start together here, and here is another chord, and this here is another one, and you can see the pitch and onset in time, and then you can transcribe it to the symbolic music or the sheet music. Okay, so we talk about the traditional ways of doing computations to get the transcription, but nowadays because if you use those computationals or feature extraction, there is always some errors, or it's not always perfect, because there are so many things interfering in your performance. It's difficult to detect precisely when it's the onside or the fundamental frequency. So there are always mistakes, and it takes a lot of computational resources. Then after the neural network came out, people think, okay, we can do something easy, and we don't do the computation ourselves. We don't design those normality curves, or we don't do this algebra to compute those features, but we just feed in the neural network, right, with our audio and the maybe the MIDI format or music XML, the symbolic music representations, so that if we provide the computer with this synchronized or matching audio and the symbolic music representation, we hope the computer can learn, right? The neural network can learn this process of transcription, so that if we feed it in with some audio here, it will generate those the musical notes directly. So it is a kind of lazy way, because it seems like human intelligence, like you don't understand this, like black box, right? You don't understand what's going on in this neural network. The only thing you know is that from this maybe I should use some annotation. Okay, so it's like neural network is like this black box, right? And from the input side, we just input it with the audio wave files or the spectrogram, right? If you do some computation here, or the spectrogram. And we also provide this with the music notations, right? Sorry about this. Okay. And then on this output side, we expect if we give it another kind of audio wave file or spectrogram, it will generate those music notations. Yeah, it's a bad drawing. Fine. So this is the what people are thinking about when they want to use neural network for the transcription tasks. So here is a work by Google Magenta on this topic. So this is on-size and frames dual objective piano transcription. Yeah, well, I'll add this to our course material later on. Yeah, I forgot to do this. But let me drop this in our chat so that you have access to this file. Okay. Oh, so this is let me see, what is this? Yeah, piano transcription with onsets and frames. I don't think it give us any information except for a performer playing music. So here it gives us some descriptions on this. Yeah, there's a paper on sets and frames. It talks about what's the methods they use in developing this model. Okay. Dual objective piano transcription here. Yeah, polyphonic piano music transcribed by deep convolutional and recurrent neural network, which is trained to jointly predict onsides and frames. So there is two, it's called dual objective, right? There's two objective functions, which is to optimize the model to predict the onsides, and the other is to predict the frames. If you're interested, you can read this paper to see what method they use. So let's see the examples. So this is what the input audio. This is the transcription. It sounds good, right? Especially they amplify the gain, right? Did you recognize this? But this is actually a common use technique in this modern music production. Is that the louder you amplify your tracks, the better kind of audience feedback are. So the audience like the louder tracks. So people sometimes use this trick, they play this thing like in a lower volume, but play this in a louder volume so that you have an immediate feeling that this one is better than that one. This is a kind of a trick. This is maybe related to psychoacoustics. Yeah, if I find some resources on this, I can share this with you. But this is a common known, a trick played by those music producers nowadays. When they mix in the tracks, they tend to amplify everything, give these compressions and like that. So let's listen to this next example. Let's listen to the transcription. Right, so it's similar here. This is quieter. This is louder. So you kind of have this feeling, this psychoacoustic, perceptual feeling that this is better than that one, but actually not. Okay. Yeah. Except for that, actually, the neural network transcription here in the examples, they actually give much better performance than what people do using those traditional methods introduced here, okay, like novelty curve and the chroma graph, because these methods are computed by human, and it always it kind of lost too much information there, and it's not precise. It's kind of based on estimation. I estimate when the note is on, and I estimate the pitch. It's not always precise, but if you use neural networks, yeah, it leaves out all those computations. It computes automatically in the black box of neural network. So yeah, like many other applications, like NLP, right, natural language processing, and all other tasks, this transcription, the neural network gives much better transcription than the traditional, engineering method that people used, for decades. So let's look at yeah, what they did with this model, right? So it's called dual objective, which means it has two loss functions. Okay, one is the frame. So the input is that this is the audio waveform. This is a log male spectrogram. we'll talk about this later on. What is log and what is male, and why they use log male spectrogram. But in general, it's just similar, like, time domain to frequency domain. This is just some frequency, something in frequency domain that you know where the pitch is. Okay. Then it's fed into this convolutional stack, convolutional neural network FC sigmoid, and it's used by LSTM, which is recurrent neural network. Put it into another sigmoid and do some predictions. And this is frame loss. So here it predicts the frame. And here is similar structure, but it predicts the onset. So the onset prediction means when. So I'm predicting when it should be right when the node is on. Importance of each model output based on onset detector. So based on my understanding is that this is one from the onset side and one from the frame side. Within the frame-based loss term, we apply a weighting to encourage accuracy at the start of the node. Based on the weight vector assigns higher weights to the early frames of nodes. The model is incentivized to predict the beginnings of nodes accurately, preserving the most important musical events of the piece. So based on my understanding is that it gives these two loss functions. So one is for the model to predict if there will be a node, and another is to predict when the node is on. Yeah, if I remember this correctly, it should be like this. But if I say something wrong, so don't believe me. Yeah, this is an old work. Yeah, I read it like a few years ago. The frame results after being restricted by the onset detector. Okay, so yeah, I'm not going to get into too much details here, but feel free to read this page and the paper. How come they used cross entropy loss in this case? The categories, because this is symbolic music, right? So symbolic music, if you think about MIDI, it only has 128 notes, discrete notes. So these are the scales. These are discrete notes here. Okay, you only have sorry, should be okay. There is only 128 numbers. Okay, so this is the category they use. So they're predicting which number it is. And for the onset, I think you're correct, but the time is not really, so they can divide the time into very, very small pieces, like a microsecond, or milliseconds, so that it sounds, the time can be very, very, very much decretized, but it's still decretized. That's where the catalog, the categories come from. So nothing is really continuous. Because they are predicting by frames, in each frame, the number of times, okay? The times are also discretized of these equal intervals, right? So there's always a limited number, be it 200, 500, even 1,000. This is still limited numbers so that they can make categories, of those things and predict using cross entropy loss. So this is a not very difficult training of neural network. I would say it's pretty preliminary, and this work was done in 2018. Yeah, it's not even a recent work. So I think they got some improvement on this later on. Yeah, but this is basic ideas. So whatever. For this work, actually they have if you go to the studios or demos, yeah, should be demo. Actually, you can play with this application. Yeah, either through the notebooks. So they give this Collab notebook here. Yeah, Collab notebook, right? You can click on this and go there, play with this application using the notebook, or you can do it immediately through the website. So they have a web built-in model here. Yeah, it is one, Piano Scribe. This use onsets and frames. And if you play with this, open it, and it's loading the model, and you can drag and drop your file immediately here. You upload the file and let it do the work. We can try it. We can try it actually. Like we can. I tried to input this entire audio here, but the model doesn't work. It seems this is too long. But if we truncate or we just cut a piece of audio, we can put it into the model and test the model. Okay. So I'll do it later on. Yeah, after our break, after I fix this bug. But actually, yeah, you can also do this. I think this web-based is with much limited capacity. If you use Google Colab, I think it can kind of deal with longer audio files if you want to transcribe this. Yeah, so we will do some real transcription here and see how well this model performs, right? Instead of listening to the select example they just presented on the website. Yeah, let's do some real work later on. So let me see. Okay. So we talk about music information retrieval and these playing. And now let's maybe talk about the music XML. Okay. So for MIDI format, I'll use my own notebook I used for the last summer. So this is my GitHub. I don't use GitHub very much, but just upload this. So this is for this thing called TTSM workshop. Maybe later on. Yes, it's here. It's called Technology and Thoughts in Sonic Media. It's organized by my colleague, also PhD student here. Yeah, so last summer we had 4 workshops, and I gave this music data processing in this MIDI format, MIDI to CSV, processing and symbolic music generation with RNN, recurrent neural network. And my colleague, so Tornike is also a PhD student in computer music, and he gives neural networks for sound synthesis. So he's basically working on VAE and some audio, audio representations of neural networks. And nowadays, recently, he works more in the diffusion models. The diffusion model is really a hot topic recently after VAE, right? So this year we will have another workshop, and I will teach something based on this, but 2.0 and some updated formats of symbolic music and generation using other neural networks. And I think he will also talk about a diffusion model, because he's working on the diffusion model for like 1 year already. But I will send out the information later on when we are confirmed with those workshops. And last year, we also have this integrative study in sound and music. So these 2 colleagues are from integrative study. PhD, it's still a PhD program in music department, and they talk about the world making jazz. Yeah, some jazz music, and Pablo talked about some electronic music things. This year we don't have integrative studies. We only have computer music this year. So yeah, just some basic information. So as I said, this was used last year, but if you download this file, if you try to run this file by yourself, you will find some of the function doesn't work because the Python already updated, right? The Python always updated so many different versions, so this version doesn't compare with that version. It's always problematic, a huge problem of using Python, right? It's updated too quickly, and for whatever application you build, you have to give the file that which specific version you use in case it doesn't compile, right? So I did some modification to this and make this working fine. Recently. So I will upload this new version probably to my GitHub or our course, our lecture files, so that you have access to an updated notebook that runs, that compiles with the current Python, Python 3, I believe. So this is for the MIDI. Okay. For music XML, so I talked about IEEE 1599 standard last time. Briefly mentioned this. You can access those files here in the folder. So the IEEE 1599 standard is a standard way to represent not only music but all media format. So the innovative or the breakthrough this standard makes is that it can represent the media both in the signal file, right? Signal format. So signal format means the audio or the TV, right? So when you're watching the images, so all the images, what you're listening, what you're watching on the computer, they are all digitalized in the numbers. So here you can see, for example, here, right? It encodes all the source material, not only the sound, right? MP3, AIFF are the sound, the audio file format. So here are the text. MIDI is the symbolic format, but also it includes the JPEG, TIFF, the images, and the videos. So it encodes. It's a very broad, general kind of way of encoding those different types and make them compatible, and also synchronize these audio, these signal files with the symbolic files here. Okay. So the basic idea here is just that. So there's audio, performance, notational, structural, logic, general. So everything. So and it adopts this hierarchical structure, right? Hierarchical structure from bottom is the audio, and upwards. I think I have this one here. So the audio format is the signal format. It's digitalized to 0 and 1. In the computer, and the performance maybe in this grid. So this is upper level. It's more compact, I would say, like mid-level representation, right? And notational are something symbolic. So there you are extracting, like what we just talked about, right? Music information retrieval. You are getting those useful informations from the raw material or raw files and represent them in a more concise way, or a way that simpler or with smaller size, right? And structural logic. Logic means you have some text notations and the general things. So the idea here is that you're not only representing audio, but also representing symbolic, and you find a way to synchronize them. So when you listening to the music, it's synchronized with probably the video or the image playing, and it's synchronized with the score followers, the symbolic things you say, and all those things are encoded in a single file in this XML format. Okay. So because this is too broad, and we're not going to talk about this in detail, and I'm not an expert on this also. But the specific example I will talk about is music XML. So this is a music XML is something that's specific for music annotations for the score for the staff music representation using XML format. Okay. So here's an introduction. Music XML is a digital sheet music interchange and distribution format. The goal is to create a universal format for common Western music notations, similar to the role that MP3 format serves for recording music. The musical information is designed to be usable by notation programs, sequencers, and other performance programs, etc. The goal of this tutorial is to introduce music XML to software developers, and yeah, etc., etc. So for this one, so I hope in our lecture today, we will have time to dig into the MIDI format, which is more numerical manipulations, like the files on all the properties are kind of represented using numbers, right? Using numbers to represent symbolic music. And here, there are some MIDI compatible format here of music XML, but there are more. Yeah, of this formatting, how to format those files, how to make them looks good, right? The display of the scores. So I'll dig into the details, but it requires you to be more patient. Okay, so now we're talking about some hardcore file processing, some hardcore programmer kind of perspective. So it won't be that fun. Okay, it won't be that fun. It will be somehow boring and just looking into those it's like HTML kind of like things. So it's not immediately understandable, but you need to be patient and look through those lines, slowly and understand what is talked about. So I'll spend some time on this today. Yes, the music XML. Yeah, I also opened this here, right? So we did a kind of rough comparison of those two files last time. So you can see this music XML, or this is MIDI. This is much better formatted than the MIDI file we just saw, right? Like those lines, the beams, the numbers, and everything. It's precisely formatted. Even the position, like X, Y axis, where this note is positioned on this page, even though these details are also specifically specified and mentioned in this document. So this makes this document pretty it's pretty long, right? Pretty long, pretty complicated, and the file size will be larger, but it definitely includes more information. Yeah, but if you need those information, like you want to print a score, then you need a music XML file. But if you only care about the audio, how the music sounds, but you don't care how it looks like, a MIDI file will be a better choice, because it's just deleted all those surplus information here, right? It doesn't care where you play those things, place those things, where the beam or where the stems are, is up or down. How do you annotate those things? It only cares about how it sounds like. So for this audio part, we'll refer to MIDI files. Okay. So I think I will continue after our break, and I'll fix this bug.